Hey folks, this is Major Jones here to give you an introduction to pipelining. So this is the start of Unit 5. We're going to talk about how pipelining and memory caches can help improve the performance of our LC3 computer. So today we want to be able to sort of define what a pipeline is and two particular terms that are important to the concept of pipelining, which are latency and throughput. And then hopefully by the end of these notes, you'll be able to sort of calculate the latency and the throughput for a pipeline and compare the performance with, between a pipeline and a non-pipelined kind of process. And we'll identify, at least two limits to the sort of the theoretical improvements we might get from a pipeline. So let's dive in. A pipeline is normally kind of introduced with some sort of process. So we'll imagine here I've got a car factory, little assembly line. What starts off as just a bunch of parts goes through, in this case, this little example, 4 stages right before it becomes a car. It's got to get the chassis sort of built and prepped, the engine gets put in, the body of the car gets attached, and then it's painted, and then we're done. And each of these little stages takes some length of time in order to complete. And so in a non-pipeline factory, right, one group of parts goes into this first stage, to have the chassis assembled, and no other car can get started until that vehicle is all the way to the end. Once that first vehicle finished and is a complete product, then we take another group of parts and send it into this pipeline. And that is not unlike the way our current LC3 runs, right? Once we start an instruction, we have to wait for the LC3 to totally complete processing before we start the next instruction. So latency and throughput are two ways we might sort of analyze these processes. Latency is the length of time it takes for a thing to move through the entire process from start to finish. So the latency of this car factory, which is non-pipelined, is 6.5 hours. We get that value here by adding up each unit of time for each of these stages, right? 1 plus 2 plus 1 plus 2.5 is 6.5 hours. The throughput is how many cars we get per unit time after the first car gets through. And in this case, the throughput happens to be the same as the latency because we're not doing any sort of pipelining. So we get exactly 1 car every 6.5 hours using this non-pipelined car factory right here. Like you can probably already imagine, right? If I've got a car that's having its body put on, the rest of these units they're idle. There's nothing's happening, and very likely, if you can imagine, like in an actual factory line, right? That's ridiculous. Why would I sort of halt these stages if I can put them to use working on other cars? So the idea of the pipelining, right, is that I've got I'll start with my car parts. They'll move into this first stage here to have the chassis built. When that first car moves on to the next stage to have its engine built, I can then put the chassis stage to use immediately by getting the next set of car parts. And so there's in this pipeline then, when the first car rolls off the end of the assembly line, having just finished its paint job, there are sort of portions of cars all the way through this pipeline. There'll be, also a car that would have just finished body work, a car that would have just had its engine put in, a car that would have just finished its chassis. And so each of these cars can sort of move into the follow-on stage as it clears out. And this is a huge boon to production, right? So the latency in this case is still the same because I haven't done anything to affect the length of time each of these stages take. It still takes 6.5 hours for a single car to get through my whole pipeline. But I get far higher production using the pipeline factory than I did with my non-pipeline factory because essentially I can take kind of the longest time here. In this case, it takes the paint 2.5 hours to complete. Well, that means that every 2.5 hours I can move a car from one stage to the next. So every 2.5 hours, I have a new car coming out of my paint stage and is ready to be sold. So instead of having to wait 6.5 hours for every car, I only need to wait every 2.5 hours, at least once my pipeline is full of things. And that's a pretty incredible performance increase, right? All I've done is just sort of, I haven't changed the underlying assembly line at all, but I've been able to increase my production by 2.6 times. And I get 2.6 as a ratio of 6.5 hours to 2.5 hours. Okay. Now theoretically, I want to talk about this note right here. Theoretically, if I separate my process into 4 stages, then I should be able to have a 4 times increase in my production. I don't get that down here, and part of the reason is because we use the term balanced to describe whether or not the stages take the same amount of time or not. In this case, the stages are not balanced, so the performance increase by pipelining my car factory is kind of limited by the fact that I have to make each stage 2.5 hours long to account for this last one, the paint stage that takes 2.5 hours. So although I can put cars into each stage in my pipeline, if I have a car here that has its body work being done, an hour later the body work's done, but the paint stage is still processing, and so the car sitting here in the body stage has an hour and a half where it's kind of sitting idle, waiting for the follow-on stage to kind of to clear up. If the stages were balanced, we would see a much higher performance increase, but it's sort of limited by the fact that these stages are not balanced. So that's important to note. Okay, so here's how this might look for. Here's what this might look like for a circuit. So let's do the same kind of thing, but now we're looking at here a 4-bit adding circuit. So going back to E360, right? I've got a half adder chained into 3 full adders. So I can take 2 4-bit numbers and add them together to create a result. And the diagram, this thing up here and on bottom, these are my 2 registers. So I have a register here that sort of stores my 2 4-bit numbers that are being added together. And then on 1 clock cycle, those 2 values will kind of go through my adders, and then the follow-on register will store the result. And this is not unlike really how our LC3 works. You can imagine that basically my memory, my registers, my instruction register, my program counter, they're all registers, they're all forms of memory. And on each clock cycle, you could almost define the LC3 as information moving from one register to another, right? Information comes out of memory and goes into the instruction register. Information comes out of the instruction register, to the control unit. Information from R0 goes into R1 or something like that, right? So this is kind of representative of our LC3. And so for this example, we're going to assume is that our half adder has a propagation delay of 15 nanoseconds. The full adder has a propagation delay of 20 nanoseconds. And the D flip-flops that I'm using here have propagation delays of 5 nanoseconds and setup times of 5 nanoseconds. Okay, so this is going back to the lesson on time parameters from the E360, right, that were a little difficult, I think, for some of us back then. So I want to just review really quick, right? Propagation delays is basically a measure of how long it takes for a signal to move its way through a device. So in this diagram here, you can see once my input changes to some electrical device, there is a propagation delay that that I have to wait before the output reflects that change, and that limits how fast I can run my circuits. So my adders, my half adders, my full adders, including my flip-flops, they all have propagation delays. And then for my flip-flops, I also have to worry about this thing called setup time, right? This was the sort of the window right in front of my clock edge when my signal could not change. Otherwise, my flip-flop might go into sort of undefined behavior. So these values affect kind of like how fast the information flows through this circuit here. This is equivalent to kind of how fast each of these stages took in our factory, and they affect the latency and the throughput, right? So let's calculate that. So the latency for this circuit here is I have to add how long it's how long it takes information to get out of this first D flip-flop. So the propagation delay for my D flip-flop. After that length of time, the 2 4-bit numbers I'm adding are present to all of these adders. But this adder doesn't get its information until this half adder has completed. So I add the propagation delay of the half adder to figure out how long it takes information to get here. Well, now I've got 3 full adders, right, that are all kind of chained next to each other. So I have to wait for information to go through this full adder, and then this full adder, and then this full adder before this last bit is known. So I have the propagation delays from 3 full adders to account for. And then this bit has to be ready prior to the setup of this next clock edge, right? So if I add all those together, that means 85 nanoseconds. It takes 85 nanoseconds for information to go from this register to this register. And that's the latency of the circuit. That's how long it takes, information to go from top to bottom. And in this version, it's non-pipelined, right? So the throughput is I get one addition result every 85 nanoseconds. How we might pipeline this is to consider the fact that each of these adders, are almost like stages in our circuit. So I could sort of break this up. I could do my half adding in one stage, and my next stage I could do the full adding of the next bit. In the third stage, I could do the next full adder, and then the last stage, I could do the last full adder. So I could sort of turn this circuit into a pipeline with 4 stages, just like I had my pipeline over here for my car factory. And it's I just have to put a little register in between to sort of store the intermediary results. Okay, in this case, my latency is actually goes up a little bit, because I have to account for I have more registers, so I have a higher number of propagation delays plus a higher number of setup times. So my latency is actually 115 nanoseconds compared to 85. But my throughput gets much better. And the reason is because for my throughput, I can run my clock much faster. Instead of having to wait for half adder and 3 full adders to complete before my next clock edge, I only need to wait for the full adder is I think the longer propagation delay in this example, right? 20 nanoseconds. I only need to wait for one D flip-flop propagation delay, the propagation delay of my full adder, and the setup time of a D flip-flop. Those are the only 3 things that need to happen between each clock cycle. So if I add those up, so 5 plus 20 plus 5 is 30 nanoseconds. I can get one of my results every 30 nanoseconds, right? I can trigger my clock every 30 nanoseconds. Once this pipeline is full, then every clock cycle I get the result of a new addition. So now I get one answer every 30 nanoseconds as opposed to one answer every 85 nanoseconds, and that's a 2.8 times performance increase over my non-pipelined adding circuit up here. So again, pipelining gives us a performance boost not by changing any of the underlying circuits, just by sort of separating the flow into stages and trying to make sure that every stage is being utilized 100% of the time. This pipeline does not achieve the sort of theoretical performance of being 4 times faster, because partly, for one, the stages aren't balanced a little bit, right? My half adder has a shorter propagation delay than my full adders. But also because you'll notice when I had to calculate my latency, right? Like I had to, in each stage had to account for the fact that there's a propagation delay and a setup time for each of these D flip-flops. And so in this case, that's kind of the limiting factor that prevents me from getting that theoretical increase. And so we can see that kind of down here. The general formula, right, is if I have a non-pipeline process, I should be able to increase my performance by the number of stages I have. But that assumes, number one, that things are balanced, and also it assumes that there's no sort of setup time around these stages that I have to account for. So you can see in this graph here, this is I'm taking some on the horizontal axis down here, I'm playing around with the number of stages that I have for my adding circuit and what my performance increases are. You can see that this is sort of asymptotically approaching some speed up even as I increase the number of stages to a really high degree, and that's because even if I were to increase my stages a bunch and I could get the propagation delay of each stage down really low, I would still have 10 nanoseconds for my flip-flops that I have to worry about. All right, so the theoretical improvement is a function of just the number of stages that I'm able to add, but it's limited based on these 2 factors, whether or not the actual stages themselves are balanced, and in a digital circuit, it's limited by the fact that the more stages I add, the more flip-flop propagation delays and setup times I actually have to contend with. Okay, so that is pipelining. What we're going to do clearly for the next couple of lessons is talk about how we might apply this to our LC3 computer. That's all I got, folks. I'll see you next time.